Hi everybody, my name is Luke D and I'm teaching a class with Paula Hauser at Nueva, and this is Biology 1, not how you pronounce it, but this is your first lesson on what biology is. So, biology literally means the study of life, but what the heck that means is a much bigger question because nobody actually knows what alive means. The biggest debate right now that we know about, that a lot of you are facing, is the coronavirus, for example. Some people argue that it is a kind of life. Other people argue that it isn't. It can copy itself. It contains information. It can pass on its information to its children, roughly. Those children can infect and do things on their own and then make other children. So in many ways, people think it's alive. But biology isn't actually about deciding what is alive and what is not. That's more of a legal question. An important one, a really, really important one, but it's not really a biological question. So if we want to think about what biology is, it's helpful to think about what a child is. So if we take an unborn child, a child within a womb, within a woman, and we think about what's actually happening. Essentially, roughly, oversimplification, I can take a woman, put her in a safe place, give her water, air, a bunch of peanut butter, some vitamins, and she will create another human being within her. And if you ask that woman exactly what she's doing, she doesn't wake up every day and say, hey, I'm going to make a liver today, or I'm going to make a lung today. Instead, she is operating under a set of biological rules, or rules that she somehow knows, that kind of create this organism on their own, which is a crazy idea. One of the most interesting aspects, I think perhaps for me, the most interesting aspect of life, is that it is self-organizing. And you see tons of self-organization in biology. What do I mean by that? You take enough of these little pieces and you put them in the right place, so for example, sperm and egg, and you put them together, they will roughly create a human being all by itself. And you see these types of systems all over life. You see them in behaviors, in political, the way humans herd themselves. You see them in grooming behaviors. You see them in flocks of birds. You see them in the way ants act. You see them in the way wasps swarm. And the interesting thing is, like, if we take that flock of birds, the flock of bird, there's nobody saying to the flock of birds, hey, this is how you should act. And the flock of birds itself isn't saying, I'm going to grab this one bird and this other bird and put them in a system together and to get them to work. But actually, the information for the flock of birds, the information for how to build a human, the information for how to get an ant colony to act as one, is contained within the units. So let's take the bird example again for just a second. Like, if we were to take a bird and we were going to say, give it a set of rules, a small set of rules. Hey, bird, if you see another bird and it flies within 6 feet of you, start following it. Bird, if the bird that you originally followed is flying in a relatively straight line, continue to follow it. And if it veers more than 30 degrees to one direction, stop following it. And bird, when you are following this bird, make sure that you are not following it directly in front of you, follow it off to the side, and make sure that you're not within 10 feet of a bird on either side of you. Now, if you take those rules, give them to that bird, and put a bunch of these birds together, what you'll actually end up is with a flying V. You can take a program, by the way, if you want to play with this idea, called Net Zero, and you can try to build a bunch of self-organizing systems and alter the parameters. But the fascinating thing about that flying V is that the information for the V, the flying formation, is actually within each individual unit. And similarly, the information for all of life, all of it, is within the individual units which comprise it. So there are really simple sets of units that comprise life. There are proteins, there are carbohydrates, there are nucleic acids, and there are lipids. Let's go ahead and throw water in there because that's really, really important. And each of those pieces, each of those individual pieces has enough information within each of them that when you put them together, they roughly self-assemble into these massive structures. Structures like woolly mammoth, or platypi, or fungus, or pizza makers. And so what we're going to start looking at first in biology is those little pieces and how to decode the information that's within each of them. So if I were to take a really classical example of a organized piece of biology, we could look at DNA, and what we could see here is that almost any part of the DNA in this middle here, so if we were to look at this middle section of DNA, governed by a very, very simple set of rules. This part is going to be attracted to this part, and when they're attracted, they're going to stick together. So one way of finding out exactly why they stick together is looking at them more closely. So I could look at this part here, and then I could look similarly at this part here, and what I would find is more often than not, when they come together like that, one is positively charged and one is negatively charged, and they come together. And what you're going to find is that so much of biological behavior can be governed by this really simple and easy principle. Things that are attracted to each other come together. And they're generally coming together because of the way they're shaped, so they fit together nicely, but also because they're oppositely or complementarily, charged in opposite ways. So what we're going to start looking at first is those first four molecules that I talked about and water, and then we're going to start looking at the charges, and then I'm going to show you a couple examples of how making small changes in those charges in a single molecule can have as drastic of effect as something like of a massive opioid crisis. It's a crazy idea, I know, but that's what we're going to get into. I also want to talk about what biology is as a study. So we said it was a study of life, and I said more than that, it's going to be the study of these molecules and how they interact with each other. But there's also what you do, or the purpose of biology. So essentially there are four purposes in biology. And there are more than this, of course, but to simplify it, I'm just going to say that there's four. There is the translational side, the academic side, the sum total we're going to call the biology textbook, and then there's going to be the education side. Okay, so what do each of those mean? Well, let's take the textbook, for example. The textbook is what most people think of when they think of biology. The textbook is a set of information generated by lots and lots of research that a bunch of people have agreed on and put together in writing. Now, these are all theories because we know they're not 100% correct, but we're pretty sure they're like 95% correct. And so we put all of this information together in academic journals, in videos, in textbooks, and all the brains of all the scientists out there. And that's the sum total of biology knowledge. However, that is not biology. That's only a small part of it. There are two other kind of like searching aspects of biology. One is called academic research, and one is called translational research. So academic research is the idea by which scientists just pursue information. So let's say I just see my ants, and I start thinking, how do these ants know how to communicate? And I start asking further questions. Well, maybe they communicate by scent. And so I alter a scent and then see if that scent alteration changes the way my ants act. And in that way, I'm gaining new information. So I'm asking questions that have not been answered before, not the ant question specifically, but maybe something like, how do we defeat the coronavirus? Or can we use the coronavirus machinery to make new proteins that we can use for, I don't know, who cares? Just new proteins. That process of academic research is one of my favorite things. It's actually probably my most favorite thing, and it's usually what I'm teaching here. The other kind of research is a little more focused. So the difference between academic and translational research is that academic research is done for the pure pursuit of knowledge. We pursue every question that we can come up with. And once we answer that one, it generally generates another question, which we then follow up. And then hopefully some of this information in the future we put into a textbook, and that textbook can be accessed to generate this other kind of research, which is translational research. So translational research is the type of biology that you do when you're trying to solve a specific problem. So right now, as we're looking at the coronavirus crisis, trying to come up with therapies or antivirals or anti-inflammatories or masks, that's all translational research. It's research with a very, very specific outcome in mind. So one of the most common examples of translational research is the pharmaceutical industry. Huge, huge translational research entity. And then the final piece, and probably the most undervalued piece or the most underknown piece, ironically, about biology, is the education piece. It does not matter what you discover or what you learn as a biologist. If you cannot share it, it dies with you. And I think this is one of the most fascinating things about biology. It doesn't matter how much you know. If you can't communicate it and you can't get other people to believe it and understand it, it does no good. And we're seeing tons of examples of this right now. People that are refusing to get vaccines or believing that coronavirus was created in a laboratory. You have people like Dr. Anthony Fauci, who is doing an incredible job of educating, and people like Trump, who might not be doing as good a job of educating, perhaps because he's ill-intended, or maybe just because he doesn't know quite how to educate somebody else. Anytime you are learning biology, translational, the textbook, or academic, one of the main things you should be thinking about is, how would I explain this to another human being? How would I share this information? Because it's in the sharing of that information that's actually going to be the power. There are tons and tons of researchers out there that look at how we share biological information and how we don't share biological information, and the massive pitfalls that creates. There are millions upon millions and millions of deaths in this world right now that are completely preventable because, believe it or not, as good of an academic or translational researcher as I am, if I'm not a good educator, if I'm not a good communicator, if I can't go to Washington and enact some legislation based on the things that I'm learning about the opioid crisis, well, then that information does no good. I'm looking forward to a really good semester with you guys. Yeah, well, I hope you enjoyed this class or this lesson, and I hope you enjoy the semester.